Welcome to our revision program for this morning. You may recall that this is the second part of our Term 2 mathematics revision, and in this part of our program, we're going to be focusing on calculus. My name is Cyril Goldstone. I teach at Blobergrant High School, and I'm very happy to have your company this morning as part of our telematics program. I also want to extend a special welcome to all the teachers that have tuned in, as well as parents as well, that are overseeing their children's work from home. Matrics, we know you're in a very interesting phase of your schooling. There have been disruptions in connection with COVID-19, but we want to encourage you to keep going. We are with you all the way. Our program this morning is a continuation of what we did when we focused on the first part of this revision program. You may remember in the first part, looking at the monitor, there we had a look at our revision booklet. And in the revision booklet, analytical geometry in paper 2 amounts to 40 marks. We mentioned that. And then functions have a total of plus minus 35 marks in paper 1. And now differential calculus comes up for examination, plus or minus 35 marks. So it's a very important part of mathematics paper 1. We also recognize, grade 12s, that this is the first time that you've done calculus. And there are a lot of concepts that are new and strange things are happening in terms of mathematics. I know many learners often battle with calculus to try and get their head around what's really taking place. Keep going. We know you're doing your best. We want to encourage you. Do not give up and do not give in. All right? And we're going to help you in that regard. Firstly, in our program, let's have a look at the overview of this lesson. We're going to consider differentiation from first principles. That was a mathematical sequence that was introduced to us by Sir Isaac Newton. Then we're going to have a look at the differentiation rules and how we simplify certain expressions. We're also going to look at sketching the cubic graph. And then we're going to have a look at determining the equation of the cubic graph, as well as determining the equation of a tangent to a curve. And then finally, we'll examine stationary points and the point of inflection. Now, grade 12s, we just want to mention at the outset that, as you know, in the normal school curriculum, 3 weeks is devoted to calculus at school. We have this program, which is a revision program that is only an hour. There is so much that you have to do in terms of revising. This will present the essentials. But over and above this, this should inspire you to keep going with your onward mathematical advancement. Noticing the monitor, our first point, differentiation from first principles. And this formula you'll find on the information sheet in paper 1, f dash x, some say f prime x, I normally say f dash, is equal to the limit as h approaches 0 of f of x plus h minus f of x over h, right? Very important, grade 12s, you must have this formula correct. Now, let's take an example as to how this really plays off. We are given a question here. The question says, we are given f of x is equal to 4x. And we are asked, determine the first derivative, or f dash x, from first principles. How do we proceed? Step number 1. We start with the formula as it appears on the formula sheet. And there we have it. F dash x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. The next line is where we substitute. Where x is, we put x plus h. And there we have our f of x over h. When we multiply 4 times x, we're going to get 4x. When we multiply 4 times h, we're going to get 4h, and we're going to have minus 4x. Notice this zeroes that out, and therefore in our numerator, we're going to have 4h divided by h. H is a common factor in the numerator and denominator, so they cancel each other out, and so our final answer here is 4. So in other words, f dash x of this is simply 4. This is the process of using first principles. In other words, it's the long way around. And it comes up for examination for 5 marks in paper 1. So it is important that we know how to use this particular format. Let's look at another example. Now we go to a quadratic function. Remember, in example number 1, we looked at a linear function. Now we are given f of x is equal to 4x squared. And we are asked to find f dash x from first principles. Step number 1. We must start with the formula as it appears on the formula sheet. F dash x is equal to the limit of as h approaches 0 of f of x plus h minus f of x over h. And then when we populate that x plus h is going to be here minus that. Don't forget the square there because that is squared. And when we expand this, we know from our expansion, right, that we're going to get x squared plus 2xh plus h squared minus 4x squared. When we multiply this 4 there, we're going to get 4x squared. Multiply this, we're going to get plus 8xh. Multiply this 4 by h squared, we're going to get plus 4h squared. And there we have our minus 4x squared divided by h. Then we take out a common factor of these two, zero each other out, and we're going to be left with 8x plus h. And when we substitute the 0 in there, which we must show, we're going to get the answer f dash x is equal to 8x. Moving on to example number 3. Now we come to the cubic. Remember, we started with the linear, we went to the quadratic, now we're at the cubic. We are given that f of x is equal to 4x cubed. We are asked to determine f dash x from first principles. Step number 1. We start with the formula on the formula sheet. F dash x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. When we substitute x plus h in there, well, now we're going to get a very, very interesting situation, right? We'll obviously have to break this up into 3 brackets and first find the product of the first 2 brackets and then multiply by the third one. In the end, we'll get x cubed plus 3x squared h plus 3x plus h squared plus h cubed. When we multiply the 4 into each of these terms here, we're going to come up with this numerator, 4x cubed plus 12x squared h plus 12xh squared plus 4h cubed minus 4x. Minus 4x cubed, positive 4x cubed will zero each other out in the numerator. Then we take out a common factor in the numerator of the h, which will cancel the h in the denominator. And when we substitute the h for 0 there, that's going to 0 out there. That's going to become 0 there. And our answer is simply 12x squared. That has been the process of determining the derivative from first principles. But what about when we deal with more than one term? Well, look at example number 4. We are given f of x is equal to 3x squared minus 2x. And we are told to determine f dash x from first principles. Remember, we start with the formula on the formula sheet. And what's very helpful in this case, because we've got a whole lot of activity happening here, well, we can even prime them before. In other words, we can find out f of x plus h first, and we can resolve that. And notice I've done it here. And to simplify that, it's 3x squared plus 6xh plus 3h squared minus 2x minus 2h. In other words, when we put in the x plus h wherever x is there. And then we're going to take that and put it into our formula here. And when we zero things out, well, we're going to land up with our final answer, which is 6x minus 2. Right? That's example number 4, differentiation from first principles. As we mentioned in grade 12s, this is an important point that comes up for examination. It's 5 marks in paper 1. So we recommend that you do as many examples as possible so that you are skilled, you are proficient, you know exactly what to do so that you can get your 5 marks. We also want to highlight now the various formats in which we can find the derivative. Now, if you notice the monitor, there are different ways of writing the derivative. We had f dash x. We can also have capital D subscript x. Then we can have dy over dx, or we could have d over dx. All these indicate ways of writing the derivative. And so let's look at some examples. If we are given f of x is equal to 4x cubed, we know how to go about this, right? If we notice here, on the sheet of paper that I have in front of me, we are given f of x is equal to 4x cubed. Now, if I have to find the derivative of this particular function, well, f dash x is equal to, I take my exponent of my variable x, and I multiply it by the coefficient. So in other words, 3 times 4 will give me 12. I still have an x here, and then I must subtract 1 from there. And therefore, 3 minus 1 is going to be 2, and that is going to be my answer right here. This is a nice, easy example, but in principle, that is how differentiation goes. And if you look at the monitor, there you'll notice that this is given us right here. Okay? And the same principle applies, but notice how we write this. There we have d of x. We are told to find the derivatives. So in other words, if you're given something like this, your answer should simply be is equal to 12x squared. What if we are told, find the derivative of y is equal to 4x cubed? Notice it's all the same answer here. So now we're going to write dy over dx is equal to 12x squared. And then if we're told d over dx and square brackets, and inside there we have 4x cubed, our answer will simply be, like this one here, minus 12x squared. So those are different ways of writing the derivative. Now, grade 12s, let me tell you a little secret about finding the derivative. In other words, differentiation. And your teacher probably explained that calculus as a body in mathematics, a body of knowledge, involves two main processes. In the South African school system, we deal with one of them, and that is differential calculus. And the other part is what we call integration. Those learners who do technical mathematics also do a bit of integration as well. Very interesting. So you may want to also have a look at that, although that does not come up for examination in the grade 12 mathematics exam in the current syllabus. We want to focus on differential calculus. Now let me tell you a secret about finding the derivative. In order to find the derivative, and if we want to make the derivative our friend, we must find out what the derivative does not like. Just like if you've got a friend, a very good friend, you love spending time with this person. You also want to find out what this person does not like. Now, differentiation does not like R, B, D. You got that? R, B, D. In other words, the R stands for root signs. The B stands for brackets. And the D stands for dividing lines. If you notice the monitor, this is clearly sketched for us here. When differentiating, in other words, before we find the derivative, remember the following. Make sure that you remove any R, B, D. In other words, before you find the derivative. We must remove any root signs. Any square root, any cube root, any root sign must go. Next, we must remove any bracket. In other words, we must multiply things out so that there are no brackets before we find the derivative. And then thirdly, there must be no divide lines that involve the variable that we are differentiating by. Divide lines over the variables. So remember that, R, B, D. What are we really saying in practice? Well, let's have a look at this example. Here we have example number 1. Remove root signs. That's the R. Notice what we are given here, grade 12s. We are told determine dy over dx if, here we have a situation here, right? Y is equal to x to the 6th power over 2 plus 6, the cube root of x squared. Now, I'd like you just to focus on this paper in front of me. We are told here that y is equal to x to the 6th power over, let me take my ruler, very important, over 2. And then we are told that this is plus 6. And now we have a cube root. There's our cube root of x squared. Now remember, calculus does not, in fact, differentiation does not like R, B, D. We've established that. I've got a dividing line here, but I must sort it out, and I've got a root sign here. So what I'm going to do now, I'm going to simplify this in such a way. Notice my next line. Y is equal to, there's an understood 1 here. I think you can appreciate that. So I'm going to shave away the fraction. So I've got a half I'm going to have here, and I'm going to have x to the 6th power, right? Notice how I made this from that. Then I've got here plus, I've got 6 here. There's nothing I can do about that because that's a coefficient. It's like the half. But this is what I can treat. I've got here x, And that remains in my numerator, and because that's the cube root, that becomes 3. So I have this particular situation right here. And now, grade 12s, I do not have a root sign, I do not have any brackets, and I do not have any dividing lines. Take note that this half has got nothing to do with the x, so that's why I don't count this as a dividing line. This is more a coefficient. It's more a number, right? So this is not the dividing line. So I am now ready to differentiate. And the way I go about this is I say, therefore, dy over dx is equal to, and as you know, I take my coefficient, 6, multiplied by a half, and I can hear you saying it, yes, it's the number 3. Then I take my x, I must subtract 1 from here, 6 minus 1 is 5. Then I take my next term, right? Notice here that's a positive, there's also positive, so I put a plus there, boldly put a plus. If I take 2 over 3, I take my calculator, and I say 2 over 3, and I multiply that by 6. The calculator will tell me that the answer is 4, so I'm going to have a 4 here. And then I have an x here, and then I've got a coefficient, 2 over 3, so I must subtract 1. Well, that's a bit of a difficult thing to do for early morning, so let me do it on the calculator. And there I have minus a third. Right. And if you notice the monitor, grade 12s, there you'll notice that this solution here is also shown for us very nicely on the monitor right here. There is our answer for this particular situation here. On the monitor, there you find dy over dx is equal to 3x to the 5th power plus 4x to the minus a third. Now, grade 12s, looking at this particular answer, if you look down at this page as well, there's a couple of things we need to talk about. Notice we started with the opening statement that they gave us. We asked ourselves, are there any R, B, D? Are there root signs? Yes, there's a root sign there. I had to get rid of that. Is there a dividing line? Well, not really. That was more of a coefficient. So I just cleared it away so that I can see what's happening with the x. And there were no brackets there. And that's how I got it very nicely, and I got this. Notice this particular format here, x to the minus a third. There is no problem in leaving your answer like this. But I want to stress this important point. If your question says, express your answer with positive exponents, well, then you'll have to express this particular answer as a positive exponent. But other than that, you can leave it as x to the minus a third power, right? That was our example number 1 that involved removing any root signs. Moving to example number 2, removing brackets. We are told if y is equal to x plus 2 all squared, determine this particular one, right? Now, there we have this. We know from grade 10 mathematics, if we have y is equal to, brackets, x plus 2 all squared, right? Now, a quick way of doing this, as we know, we have y is equal to, you take the first, there are 2 terms here in brackets. You take the first one squared, so x times x is x squared. Then you go for your last one squared, positive 2 times positive 2, that's positive 4. Because there's 2 terms in the original bracket, you take the number 2, and you're going to multiply it by the first one. So 2 times x is 2x. You take that product, you multiply it by the next one, which is positive 2, and there you get plus 4x. That's a quick way of solving this. I'll take you through that once again. The first one squared, plus the last one squared, plus you take the number 2, multiply by the first one, take that product, multiply by the second one, and there you get it. Once we have this, now we can find the derivative. There's no root signs, there's no brackets now, there are no dividing lines. Therefore, dy over dx is simply here. 2 times 1 is 2. We're going to have x, and that's minus 1. Then we're going to have 1 multiplied by positive 4. We're going to have plus 4. And there's a 1 here, 1 minus 1. That's going to be x to the power 0. We leave that out. And we know the derivative of a constant term is 0. And therefore, our answer is none other than 2x plus 4. If you notice the monitor, this is given to us very nicely on the monitor. There we see the solution clearly sketched for us there. We encourage you, grade 12s, to keep doing many examples so that you become proficient in connection with finding the derivative by removing r, b, d. Look at example number 3. Example number 3 is where we have to remove divide lines. Now notice here, we are told determine the derivative as respects to x of x squared minus 4. Now we know what this represents from grade 9 and grade 10 mathematics. This is the difference of two squares. So you'll notice right here, we've actually factorized them. And can you believe it? One of those factors will cancel what is already in the denominator, and we're simply left with x minus 2. We're going to find the derivative of this, then that is equal to 1, right? And of course, as is mentioned here, we first have to factorize, and then we simplify. And notice the answer, we simply say, is equal to 1. So, differentiation. In order to differentiate, we must remove R, B, D. R stands for remove any root signs. B, remove any brackets. And D, remove any dividing lines over the variables. Very important. And then we follow the format of differentiation. We're now going to have a look at the cubic graph and sketching the cubic graph. What is involved in connection with the cubic graph? Well, notice the monitor. The standard form of the cubic graph, or the cubic equation one can say, is given as f of x is equal to ax cubed plus bx squared plus cx plus d. Notice grade 12s, if the a is positive, your cubic graph is going to look like this. In other words, it starts from the bottom and it goes up to the top. If this is negative, it starts from the top and then it comes down to the bottom. So if we look at this piece of paper that I've got in front of me here, if I draw a Cartesian plane here now, and there's my x-axis, and I draw a y-axis like this, and if I just draw a sketch, right, just to demonstrate a couple of things here, and I draw a cubic graph that looks like this. Right? Notice, because it started this way, my expression is going to be f of x is equal to, for example, minus 2x cubed plus 4x squared plus 5x, and so the story goes. You notice that? Minus, because it came from the top. But on the other hand, if I draw another Cartesian plane and demonstrate the opposite principle now, there's my x-axis here, and there's my corresponding y-axis in that particular Cartesian plane. And now, if I draw a cubic graph that goes like this, because this started from the bottom, my equation of the cubic graph would be something like this. H of x, for example, is equal to 2x cubed plus 4x squared plus 5x minus, let's say, 6. Right? There we go. Notice, because this is positive 2, it started from the bottom here. So I think we've got these 2 points very clear in our minds. Right? If we put them side by side, well, there we have the first one. There, because the graph has a negative value, right, that a is negative, it must start from the top, go down like that. Then on the other hand, because this is positive now, it must start from the bottom. There we go. This is all part of our conceptual framework, which is so important. And we need this for where we are going in terms of sketching the cubic graph. Now, if we look at the monitor, to sketch the cubic graph, we need to do the following. Grade 12s, first and foremost, we must find the x-intercepts. And when we find the x-intercepts of any equation, we must let y equal 0. In other words, that will involve factorizing. Then we have to find the y-intercept. Now, by inspection, we can just look and see the y-intercept is right here. But you can also get that if you substitute 0 wherever x is, you're going to get this value right here. And then thirdly, we're going to find stationary points. And how we do that is we find the first derivative of that cubic expression. In a very real sense, grade 12s, what we are saying is this. If you have to sketch in your minds a plan in connection with drawing a cubic graph, remember the following. You have to know how to find your x-intercepts. That's point number 1. Next, you must find the y-intercept. In fact, that's the easiest one to see because it's normally the constant term, right? So point number one, x-intercepts, then your y-intercept. Then you find what is called your stationary points. And we're going to notice why this is so important, because this is where the graph comes to a certain point, it stops and goes down, and so the story goes, right? And then we have to find what's called the point of inflection. And we're going to also have a look at that. Well, moving on, here we have our first example. Example number one says, sketch the graph of, and there we see our formula, f of x is equal to x cubed minus 4x squared minus 3x plus 18. By inspection, my y-intercept is positive 18. Do you notice my value of a is positive as well? So you know where it's going to start from. And so now, if I'm going to find the y-intercepts, I must let y equal 0, and then I must factorize, right? And in a previous broadcast, we handled how we factorized the cubic expression as well. Now, I'd like to show you how we can also do this using the calculator. If you have a look at this expression here, f of x is equal to x cubed minus 4x squared minus 3x plus 18. That plus 18, we have to find the factors of plus 18. Now we know the factors of plus 18 are 1 and 18, 1 multiplied by 18, 2 multiplied by 9, 3 multiplied by 6. Those are the factors, and then they start repeating themselves, right? Now, if we have to look at our calculator, let's have a look at our calculator. I've got my calculator in front of me, and if you look down here, you'll be able to see. When I switch my calculator on, you'll notice that there's this particular function here that's called mode setup. If you press that mode setup, and there you get three options. Number one is comp, number two is stats, we use that for statistics, and number three is table. I'm going to take option number 3, which is my table format. So I'll press option number 3. Then I see on my screen f of x is equal to. What I'm going to do now, I'm going to encode that particular cubic expression. And how I do that is I press this button, alpha, and then there's my x right here, alpha x. And then I must format that with a cube, right? So I'll get x cubed because that's in my expression. Then I say minus 4 alpha x, x squared, right? Because that's in my expression as well. Minus 3 alpha x, and then I have plus 18. And I say equal to. It then asks me for another function. I'm not interested in another function at this stage because I only want to find a start in connection with factorizing the cubic expression. So I just say equal to. I start at number 1, and a good place to end is number 9, right? And step 1, you can say, and there you'll find a table. What we have to do now, grade 12s, is we have to look at this table and try and find out where is a 0 here on this table. And when I look down at my x values, I notice by 3, there's a 0 right here. So I know somewhere along the line that one of the factors of this particular cubic equation is x is equal to positive 3. Well, notice the monitor now. I will come back to that x is equal to positive 3. But now the monitor here, once we factorize, we put 0 there. Well, there we have it, x plus 2, and there we have this particular expression here. So when we factorize that, you'll notice now that x is equal to 3 twice, as you can see, and that's what we found on our calculator. This method here was by taking another factor, trial and error one could say, and finding out the remainder is 0, and there we had x plus 2 is a factor. Notice when I substituted x minus 2 there for x, and there we have it. So now, what are we saying? Well, our x-intercepts are none other than x is equal to minus 2, x is equal to positive 3, x is equal to positive 3 again. So 2 of them are x is equal to 3. What does this really mean? Well, if we tidy things up from what we know so far, there's our expression, our cubic expression, and here we have our x. We found our x-intercepts by making y equal to 0. And the coordinates of our x-intercepts are minus 2, semicolon 0, positive 3, semicolon 0, positive 3, semicolon 0. The y-intercept, coordinates of the y-intercept, remember, the y-intercept is positive 18, so in coordinate format, that is 0, semicolon 18. What about my stationary points? Well, this is where I come back to my cubic expression and I find the first derivative. And when I do that, notice, when I find the derivative of that, I'm going to take my expression. Notice here, I have f of x is equal to x cubed minus 4x squared minus 3x plus 18. What I'm going to do now is to find f dash x, the first derivative. When I do that, 3 multiplied by 1 will give me 3 minus 1. I'm going to have x squared. 2 multiplied by minus 4 is going to give me minus 8, and I'm going to have x. And then 1, there's a positive 1 here, multiplied by 3, I'm going to have minus 3. And I know that the derivative of a constant term is 0, so I leave that out. Very important now, grade 12s, I must recognize at the stationary points, the first derivative is equal to 0. You get a mark for that when you work out your stationary points. And when I work out my stationary points, what I'm saying is if I say 3x squared minus 8x minus 3 is equal to 0. If I have to factorize that, my factors here will be 3x plus 1 and x minus 3. Let me check and see that that's the case. 3x multiplied by x will give me 3x squared. Positive 1 multiplied by minus 3 will give me minus 3. Take the innermost ones. Positive 1 multiplied by x will give me positive x. 3x multiplied by minus 3 will be minus 9. Minus 9x plus x will give me minus 8. Therefore, my solution is if I equate each of these to 0, finally I come with x is equal to minus a third, or x is equal to positive 3. Those are the x values of my stationary points. Now, what do I do with these x values? I take each of these x values and I must substitute them in this original cubic expression here, right? And notice the monitor now. When I do that, here on the monitor, I substitute minus a third into the original cubic expression. And when that x value of minus a third is substituted, I'm going to get an answer in fraction format of 500 over 27. Very interesting, grade 12. The denominator of a stationary point will always be the cube root of a certain number, or a certain number cubed will always be the denominator, right? So in other words, this denominator will always be an 8, because 2 times 2 times 2 is 8. It will always be a 27. 3 times 3 times 3 is 27, or it could be 64. 4 times 4 times 4, and so the story goes, right? Just an interesting observation. You may want to check that out for yourself. Once again, I stress, that's when it is in fractional format, all right? Of course, it can be divided by 1, and of course, we know 1 times 1 times 1 is also 1. Now, the other coordinate, x is equal to 3, when we substitute that into that expression there, well, we're going to get 0. So what are we really saying? Well, we have these very interesting points. Here we have a summary of our cubic graph. There's our original cubic expression. There we have our x-intercepts here in coordinate format. There we have our y-coordinate there. And now here we have our stationary point. Notice, grade 12s, here, there's our x-intercept, and there is our other x-intercept. That's where the graph touches in 2 places at the point x is equal to 3. And it is also a stationary point as well. Here the graph goes up, and it almost stops there, and it comes down, and it stops there, and then it comes up again. All right? Very important point. And there are the points minus a third and 500 over 27. And there we have the other point here, where we have x is 3, and the y value is 0 as well. Fine. Now, let's talk about what we have just done. Increasing and decreasing functions. These questions often crop up in the exam. We've done the cubic graph now. We've sketched that. There's one other point we are coming to just now, and that is the point of inflection. We're going to handle that in a moment. But let's first talk about what was happening with the graph. Let's start from where we left off, the stationary point. At the stationary point, the first derivative is equal to 0. In other words, f dash x is equal to 0. And the same applies here. Now notice, grade 12s, that this graph goes up like that. So therefore we call this an increasing function. It's increasing this way. Notice positive, 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 positive. When it comes to the top here, it's 0. And then it becomes negative, 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 negative. That becomes a decreasing phase or decreasing function. Then it comes here, it's stationary again. And then it comes up again here. There we have that, right? Increasing. Positive, 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 positive again. Have we got that again? Let's take it again. From here, we have positive, 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 positive. Here we have 0. That's the derivative of x is equal to 0. Negative, 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 0. And there we have positive. So in other words, we have an increasing function giving rise to what is called a local maximum. Notice, local maximum. At the local maximum, f dash x is equal to 0. Then we have the decreasing phase, and we give rise to a local minimum. And that is f dash x is equal to 0 as well. And then we come up the increasing function too. Then, moving on, we now come to the point where we have to find the gradient of a tangent to a curve. Grade 12s, an important point to remember in connection with the gradient to the tangent of a curve is this. The gradient to the tangent of a curve is the derivative of the curve at that point. Have you got that? The gradient of the tangent to a curve is the derivative of the curve at that point. With that principle in mind, have a look at the monitor. We have a question here that says, consider the graph of g of x is equal to minus 2x squared minus 9x plus 5. There we have a maximum value parabola. And in red, we have a tangent drawn. And the question says, determine the equation of the tangent at x is equal to minus 1. So they've given us a point, x is equal to minus 1. What is the equation of the tangent at that point? How do we proceed? Well, we start by writing out the original function that we are given. G of x is equal to minus 2x squared minus 9x plus 5. Then we substitute minus 1 wherever x is by saying g of minus 1 is equal to, and we put minus 1 there, and then we're going to get its corresponding y value. So we know that at this point, while the x value is minus 1, the corresponding y value on the y-axis is positive 12. And now, what we do is we find the derivative of this particular quadratic function, right? So if we find the derivative of minus 2x squared, we know that that is going to result in minus 4x, and the derivative of this is going to be minus 9. And so then we take our minus 1 and put it into x, and we get our corresponding 5, minus 5. That's the gradient of the tangent. When we take that gradient and put it into the equation of the straight line, then we'll find the equation of our tangent is y is equal to minus 5x plus 7. Very important principles. Now there's another question that we're going to explore that involves the cubic graph. That was finding the equation of a tangent to a parabola. What about to the cubic graph? Well, notice this question that is drawn from a past grade 12 paper as well. On the monitor we read the following. The tangent to the curve of the function defined by p of x is equal to x cubed plus 1 passes through the point A to K, right? And then they say, find the numerical value of K. The next point, determine the derivative of P of X, let's put it like that. Hence, determine the equation of the tangent to the function then. If we have to find the numerical value of K, what we have to do is we have to take this 2, which represents an X, and put it in here wherever X is, and then we're going to find the numerical value of K. When we look at that, well, there we have our solution. Notice we first write out P of x is equal to x cubed plus 1. And so if we substitute x as 2, we're going to have 2 cubed plus 1 is equal to k. 2 cubed we know is 8. 8 plus 1 is 9. Therefore, k is equal to 9. The next part of the question says we must find the derivative of that. There we have P of x is equal to x cubed plus 1. If we have to find the derivative of this, well, the first derivative of that, P dash x is equal to 3x squared. That's an easy one. Now when we have to find the tangent, we take that derivative, and there we find its gradient by substituting that 2. Remember, we were given that 2 in the original part of the question, and we put the x value to find its corresponding y value. And so in a very real sense, here the gradient is going to be equal to 12, because 2 squared is 4, 4 times 3 is 12. Using the equation y is equal to mx plus c, we're going to have y, which is 9. There we had it. That's the value of k. There we had our 2, there, which is our x value. And our m, which is from this particular part here, that's 12. Our c is equal to minus 15. So the equation of our tangent is y is equal to 12. 12x minus 15, right? And we can also write it in this format here, depending on how the examiner says we should write it, right? This is generally the same format. And of course, this particular solution here just represents the other equation for the straight line. This is y is equal to mx plus c. This is y minus y1 is equal to mx minus x1, and so the story goes, and that's how we get it. Okay, fine. So that's how we find the equation of the tangent. Let's look at the point of inflection. This is also to do with the cubic graph, but this is where the concept of concavity comes up. If you notice the monitor, the point of inflection occurs where the concavity of the graph changes. Now, I'd like to take you back just to the sketches that I drew earlier on. And if we have a look at this particular sketch here, right, let's take note of a couple of points. We know grade 12s, just as a brief summary now, this particular point here is an x-intercept. Not so. We also know that this is an x-intercept. We understand that this is the y-intercept, of course. We know that. All right? And we know how to get the x-intercepts. We let y equal 0. We know how to get the y-intercept. We let x equal 0. We also know that this particular point here is a stationary point of the graph. And this point here represents a local minimum. And this particular point here is a local maximum. So there's a stationary point here, and there's another stationary point here. This is a local minimum. This particular one here is a local maximum. What about the point of inflection? Well, if I have to draw in the point of inflection on this graph, the point of inflection will be somewhere here, somewhere there. And I'm going to put it as POI, right? The point of inflection. What is happening at the point of inflection? Well, at the point of inflection of every cubic graph, that is the point where the cubic graph changes concavity. In other words, it changes from a happy face to a sad face, one could say, or from a sad face to a happy face, right? The best way to describe it in proper mathematical terms is the point of inflection represents the point where the cubic graph changes concavity. And this is what we need to talk about. Before we talk about that, let's have a look at the other sketch that I drew just now. The other graph, cubic graph. Let me just find my paper here. You may recall that we drew that one as part of our conceptual framework earlier on. Here's the graph here. So if we look at this one, let's just itemize a couple of points here as well. In review, when we look at this particular sketch, we know that this point here is an x-intercept. We know this point here is an x-intercept. We know how to get that, don't we? We know that this point here is the y-intercept. There's only one, of course. Okay. What about the points of stationary points? This is a stationary point. And in terms of this graph here, the way I drew it, the stationary point will be here as well. Right? Just there. And there's stationary point. I'll just do it like that as well. Just in red. Right. So we have our two stationary points. Where is the point of inflection on this graph? Well, if I have to draw this in, the point of inflection will be somewhere here. Right? There it is right here. P-O-I. I'm just going to put it like that. That's the point of inflection. That's the point where the graph changes concavity. And that's what we are going to talk about right now. Please focus on the monitor, because here we have a very good summary as to what is meant. At the point of inflection, that's where the concavity changes. In other words, where the second derivative, notice, the second derivative of x is equal to 0. Well, what do we mean by that? Well, if you have a look at this graph, there you see the POI, right? What we say is from this point, can you see this gray part here? The graph is concave up. Grade 12s, when it is concave up, the second derivative of x is greater than 0. Please remember that important point. Then when it's concave down, notice the broken line, the second derivative of x is less than 0. Let's have a look at this particular sketch. There's our point of inflection. There we have concave down. Notice, once again, for concave down, the rule still applies here. The second derivative is less than 0. And for concave up, your second derivative is greater than 0 as well. Have you got those main points? Well, the second derivative test, we may say, is there's another way to find the nature of the stationary points. If the second derivative of x is greater than 0 at the stationary point, it is a local minimum. We found that out earlier on, didn't we? And if the second derivative of x is less than 0 at the stationary point, it's a local maximum. If the second derivative of x is equal to 0 at the stationary point, why, we have a point of inflection, right? And those are the points that we mentioned in our program so far. So in summary, let's have a look at concavity. If we notice the monitor, here we have a cubic graph. There we have our x-intercept here. We have another x-intercept here and another x-intercept there as well, right? Our x-intercept. Our y-intercept is also here as well. There we have our y-intercept because that's the only place that this graph cuts the y-axis, okay? There we go. Then, if we have this drawn up there, we know this is an increasing, plus, until we have our stationary point. That is what we call a local maximum. Then negative, decreasing, local minimum, right? And there we have it, and this is how the whole story goes, right? I see that this is the y-axis, right? So in other words, this here is where we have that entire situation there, okay? So that is our y-intercept there, okay? And we go up like that. Now, notice the detail here. The second derivative of x is less than 0, where we have concave down. And the second derivative of x is greater than 0, where we have concave up. And if we find the second derivative here, it's equal to 0, that's where the concavity changes. So just as we saw in the previous slide here, the point of inflection is where our concavity changes. Remember the point of inflection? There we have it. When we have concave up, we have our second derivative of x is greater than 0. And there we have concave down, our second derivative of x is less than 0. If we look at this particular shape here, when we have concave down, the second derivative of x is less than 0, and concave up, the second derivative of x is greater than 0. Very important principles, and that was brought over to us here. Grade 12s, in everything that we do, in calculus, in mathematics, in everything we do, let's remember to plan our work and then work our plan. We've spoken about many things this morning. We started by having a look at differentiation from first principles. Remember, to differentiate from first principles, we must start with the formula as shown on the information sheet. And the way to get our full marks for that question is by doing many examples, so that by the time we get to the exam, whatever question comes our way, we can handle that question with aplomb. Next, we went into the rules of differentiation. Remember, differentiation does not like RBD. Doesn't like root signs, doesn't like brackets, it does not like dividing lines over the variables. So before we can even differentiate, we must remove all root signs, all brackets, and all dividing lines. Take them away, and then we differentiate. Also recall that there's nothing wrong in leaving a negative exponent for x. So you can express your answer like that as well. Then we moved on to the cubic graph. The cubic graph is this beautiful graph that we've met now in grade 12. We've learned how to draw it. Also in your revision grade 12s, develop questions and work on questions where you are given the graph and now you must find the cubic expression, the cubic equation. Very interesting and very important as well. Make sure you know how to do your x-intercepts, to find your x-intercepts. I showed you using the calculator how you can get a start in connection with factors. Then you go for your y-intercept. Then you go for your stationary points. Your stationary points will represent your local minimum and your local maximum. Right? Very important. At the stationary points, the derivative of x is equal to 0. And then the final point we need is our point of inflection. The point of inflection is where the graph changes concavity. The other detail that we've covered this morning is to find the equation of a tangent to a curve at a particular point. And remember, the gradient of the tangent of a curve, of the tangent at the point, is the derivative of the curve at that point. Very important principle. So, more practice will bring us more marks. If we practice a little bit, well, we'll get a little bit. Grade 12s, we want to thank you so much for your attention. We want to wish you well with your preparation for exams. Calculus is 35 marks. Keep working on your calculus. You can do so well. Go through past examination papers. Work through study guides. Do as much practicing as possible. And as you move along, even although things may become tougher for you, do not give up and don't give in. And always remember to have integrity in what you're doing. Follow the detail, the steps that we've outlined, that you've learned from your teachers. Work in concert with all these fine arrangements. We wish you well for your preparation for the trial exam and even for your final exam. Keep working on your mathematics. And in everything you do, may you succeed. All the best. Bye-bye.